Okay, so let me show you some evidence that this actually works. So we've been interested in binders to this cancer-associated protein called prostate-specific membrane antigen. This is a protein that's very different than the standard prostate-specific antigen, the PSA test that probably many of you in this room have encountered at some point in your lives. The PSA test, if you've encountered it, is notoriously unreliable. It's associated with lots of false positives due to things like inflammation. So minor other problems can give you a tremendous fear that you've all of a sudden contracted prostate cancer associated with this PSA test. PSMA, it looks like it's going to be a much more specific cancer-associated marker because its synthesis happens only on prostate cancer cells. So there's some specificity there that we're really excited about. And a former graduate student in my laboratory, who's now a scientist at Sangamo Biosciences named Phil Tam, came up with with viruses that bind with high specificity to this protein called PSMA. And the details of this experiment aren't so important for us today, but I can tell you about them later if you're interested. But it basically shows that we have high affinity binders to the cancer-associated protein, and these bind only the cancer-associated protein and nothing else that's in our experiments. And that's a really important criteria as well, right? We want things that bind cancer and not bind normal cells. Okay, so that's step one. Step two is once you make these binders against the cancer molecule, we need stuff that's going to bind with very, very high potency. And we've recently invented a way of optimizing affinity, so optimizing the fit of the binding partners for binding to these cancer-associated molecules. And I have to tell you, we started doing this for very fundamental reasons. You remember earlier I told you how I was very interested in the hand and glove fit of molecules in the cell? Well, one way that we're using to dissect how that hand-in-glove fit works is a technique called homolog shotgun scanning. And the details aren't very important, but it's basically a way of going through and systematically altering the glove to look at how that affects fit by the hand. And it turns out, sort of coincidentally to this gave us a great way of optimizing fit. And if we can optimize fit, we can then improve sensitivity. Okay, so let me show you an example of this. So improved binding is going to give us increased sensitivity, because if the binding is better, that means we'll be better able to detect tiny, tiny little quantities of these cancer-associated proteins. And I want to tell you in advance, as a caveat, that's what we need, because there is not a lot of cancer-associated protein that's floating around in your urine. Okay? Hopefully none in the case of everyone in the audience today. But the truth is it's going to be really tiny quantities even in the case of cancer. So we need very high sensitivity. And it turns out that this homolog shotgun scanning gives us this. And again, we were doing this for really fundamental reasons. So it shows to me the value of basic research as a tool for uncovering implied things. Turns out this technique has been adopted by many pharmaceutical companies after we published it. It's actually a greatest hit from our laboratory in an unexpected way. Okay, in any case, here's the original binding partner down here with the arrow, and then here's selectance. Here's optimization, and you can see we've moved the sensitivity up several orders of magnitude. And you know, this is like a tenfold, 100-fold, 1,000-fold. That's a really big deal. If I can make something that's 1,000-fold more sensitive, that means that I only have to I can detect something that's 1,000-fold less concentrated, 1,000 times less of the cancer marker around to get the same signal. And it's a big deal to the pharmaceutical companies because that means then I can give patient 1,000 times less drug and get the same potency of the drug. And that's one of the reasons why this has really turned out to be a major success. Okay, so here's getting back now to our idea for daily diagnostics. Here's what we want to do. So what I specifically want to do is I want to set up something so that when stuff binds out here, then it results in some electrical signal over here. And truthfully, we've made a lot of progress on this.